In this warm-up, we are squaring all of these values in scientific notation. So I'm going to show you number 6 as an example. 4 squared is 16. And then with these exponents, we multiply the exponent. So negative 3 times 2, which is negative 6. But this is not in scientific notation. I need to move that decimal. So it should say 1.6 times 10. I made 16 smaller by turning it into 1.6. So I need to make my exponent bigger by 1 because I moved the decimal 1 spot. 1 larger than negative 6 is negative 5. So this is the one that's in scientific notation. Please complete the remaining 5 questions in your warm-up. Which do you think would be taller? A stack of all the planets in the solar system or a stack of the sun and moon? Well, the sun is pretty large, but the moon is kind of small. And if we stacked all the planets on top of each other, maybe it would add up to more than the sun and the moon combined. You decide, and we're going to look at some information to hopefully answer this question better later. I'm going to guess a stack of all the planets. Here, we're going to stack. Here we have the planets, and here's the moon getting smaller and smaller. With the sun. So, I said the following would be taller. A stack of all the planets in the solar system. Would you change your answer? Yes, I would change my answer. Because the sun is larger than the entire stack on its own. Here we have a breath count. We're filling up this little balloon. I have made it to 50 breaths, and I still have a long way to go before that goal balloon is filled. So we're going to try a different strategy to figure out how many breaths it would take to fill it up to its goal size. It says on average an 8th grader's lungs can hold 3.6 times 10 to the negative third cubic meters of air. What volume of air would you get from 2 breaths? Write your answer in scientific notation. So we are multiplying this by 2. Or we can think of multiplying it by 2 times 10 to the 0 power. Well, 3.6 times 2 would be 7.2 times 10 to the negative third power. Because we are just doubling this value, which we don't need to reformat it into scientific notation because it's already 7.2 is a single digit. What about 10 breaths? So if you multiply 3.6 by 10, that would give us 36 times 10 to the negative third. But that's not in scientific notation. We need to change it so that we have 3.6 If we make this smaller, the exponent needs to get bigger. So from -3 to -2. If a breath's volume is about 3.6 times 10 to the -3 cubic meters, how many breaths does it take to reach the goal? So we're trying to get to here. We could divide to split that up. And if we do that, we would have 3.6 times 10 to the 0 divided by 3.6 times 10 to the -3rd. When we're dividing in scientific notation, we divide those initial values. 3.6 divided by 3.6 is 1, and we subtract the exponents on the 10. 0 minus -3. This can be rewritten as addition with a positive 3. So 1 times 10 to the 3rd. In standard form, that would be 1,000 breaths. We probably wouldn't reach that in class time. So sitting here trying to click on breath and breathe over and over and over again, we probably wouldn't reach 1,000 breaths. And, yep, 1,000 would do it. You said it would take 1,000 breaths of 3.6 times 10 to the -3rd cubic meters to reach the goal of 3.6 times 10 to the 0 cubic meters. Complete the comparison statement. The volume of the goal is blank cubic meters. The volume of the goal is 3.6 times 10 to the 0. That is 1,000 times as much as the volume of a single breath, and the volume of a single breath is 3.6 times 10 to the -3rd. On average, an 8th grader breathes 14 times per minute. Assume you have been breathing at about the same rate your whole life. How many breaths have you taken so far? Write your answer in scientific notation. Typically, 8th graders are between 13 and 14 years old. I'm going to go with 14 years old. Now, years have about 365 days in them, which on a leap year you'd have 366. So you might factor that in by doing a quarter, or you might just use a rough approximation. So 14 years is 365 days a year. There are 24 hours in a day, and there are 60 minutes in an hour. So 14 years, 365 days per year, 24 hours per day, 60 minutes per hour. And if we multiply all of this out, that'll tell us how many minutes a 14-year-old who just had their birthday has been alive. But that's how many minutes we've been alive for as a 14-year-old. We have taken 14 breaths per minute. So we still need to multiply this value by 14 to figure out how many breaths we have taken. And it asks us to write our answer in scientific notation. This is just an approximation, so I'm going to do 1.03 and just keep 2 decimal spots. And that would be times 10 to the 1, 2, 3, 4, 5, 6, 7, 8th power. And we're going to type it in that box. 1.03 times 10 to the 8th power. And now we're going to watch what happens with this many breaths and how big our balloon would be. So, almost as tall as Big Ben, bigger than a tree, and a whale, and a house. Your life breath balloon contains those 1.03 times 10 to the 8th breaths you have taken so far. If a breath's volume is about 3.6 times 10 to the negative third cubic meters, what is the approximate volume of your life breath balloon? Write your answer in scientific notation. So the number of breaths times the volume per breath. So we will have 1.03 times 10 to the 8th is going to be multiplied by 3.6 times 10 to the negative third. When multiplying in scientific notation, we multiply those initial values and we add the exponents. So 1.03 times 3.06 is 3.708. And if we add those exponents, 8 plus negative 3 is positive 5. Now we will type that in. And we have the correct volume. In a moment, you will make a comparison statement about your life breath balloon. First, choose the type of statement you want to make. I'm going to go with a times as much. Next, choose an object to compare. How about a swimming pool? The volume of a life balloon is 3.708 times 10 to the 5th cubic meters. And we've got to figure out how many times as much as the swimming pool, which has a volume of 3.5 times 10 to the second. So we're going to do some calculations. 3.708 times 10 to the 5th divided by 3.5 times 10 to the second. Remember, we are going to divide the initial values and subtract the exponents. 5 minus 2 is 3. And when we divide 3.708 by 3.5, we get approximately 1.059. Times 10 to the third, that would move the decimal 3 spots. So that wants it in standard notation here, because we don't have that little feature to add the scientific notation. Now we are going to stack a dollar bill. About how many dollar bills will we need to stack to go from the Earth to the moon? Now clearly this distance is not to scale, but we're trying to figure out how far we would need to go for that distance. In this slide, it tells us a dollar bill is 0.11 millimeters thick. About how many dollars will it take to make a stack 1 meter tall? Round your answer to the nearest $100. Write your answer in scientific notation. Well, there are 1,000 millimeters in a meter, so we can think of millimeters as 1,000th. So this can be rewritten as 0.11 times 10 to the negative third power. And if we're trying to get 1 meter, that would be 1 times 10 to the 0. Then we would divide. Remember we talked about how we would subtract the exponents when we're dividing? 0 minus negative 3 turns into a addition with the positive. And 1 divided by 0.11 is approximately 9.091. But the question asks us to round to the $100 bills. Right now, this is 9,091. So we've rounded to the hundreds, that would be 9,100, or 9.1 times 10 to the third. And we got the check mark, so we know we've done a good job. Here it says the moon is approximately 3.84 times 10 to the 8th meters away. And we discussed that this is the same as 0.11 times 10 to the negative third meters, because we converted from millimeters to meters, so they match. Then we're going to divide these two and subtract these. 8 minus negative 3 becomes 8 plus a positive 3, so 10 to the 11th power. But this is not in scientific notation. We need to move the decimal one place. By doing that, we made the number smaller, from 34 to 3.4, so we need to make our exponent larger. And it looks like we made it to the moon. Here it says you said it would take 3.4909 times 10 to the 12th dollars to make a stack from Earth to the moon. In February of 2019, the United States national debt was about $22 trillion, or 2.2 times 10 to the 13th. Make a comparison statement between the value of your Earth to moon stack and the national debt. We are going to make a comparison statement of how many times more than. So when we're figuring out how many times more than, we use division. 2.2 times 10 to the 13th is the debt. And then we're going to divide by 3.4909 times 10 to the 12th, which is how many dollar bills it would take to stack from the Earth to the moon. We divide the initial values. 2.2 divided by 3.4909 is about 0.6302, and we subtract the exponents. 13 minus 12 would be 1. This is not in scientific notation. It needs to be bumped over 1 decimal spot. We increased this initial value, so we need to decrease the exponent, which is essentially just saying the national debt is 6.302 times the distance of a stack of dollar bills that would go from the Earth to the moon. So we could create 6 stacks to the moon with our national debt. Here it says the approximate sun and planet diameters are shown. You have 3 attempts to build a stack of planets as close to the diameter of the sun as possible. You must use at least 3 different planets. You may use up to 5 of each planet, and you may choose not to use some of the planets at all. So you don't have to use every planet, but you do need to use at least 3 different planets. I'm going to start by making these all 0, and then I'll adjust how many I want in a minute. I'm going to use the largest planets because I'm trying to get to 10 to the 9th, so I want to use some of the larger planets. I see 2 that have 10 to the 8th and several that have 10 to the 7th, but this one has a 5 and these ones only have 1.2 and this one's 4.9. So I'm going to start by using 5 of these. And I'm going to do the calculation on the side so you can see what I'm doing. My goal is to reach this amount, or as close to it as I can. So if I use 5 of those, then I'm going to multiply 5.11 times 5. But that can be rewritten as 2.555 times 10 to the 7th. I'm also going to include several Saturns. Let's go with 3. 3 Saturns, that would be 3.6 times 10 to the, so I didn't change the exponent on that one, times 10 to the 8th. And another way that I could write this is 13.9 times 10 to the 8th. If I combine these two right now, 2.555 and 3.6 together, that gives me about 6. But I'm trying to get to 13. So 6 plus about 7 more would give me 13. So I need to change 1.43 into a 7. So I'm thinking if I use 5 of those, I use 3 of these, 5 of those, 5 times 1.43 is 7.15 times 10 to the 8th. So if I add those together, I have 2.555 plus 3.6 plus 7.15. And since all of them are 10 to the 8th, I can just add up their initial values. And that gives me 13.305 times 10 to the 8th. So I'm pretty close, but I've got about 0.6 more to go. So let's add a Neptune. I can rewrite this as 0.495 times 10 to the 8th. So 0.495 times 10 to the 8th combined with these, the 3 from before, 13.305 plus 0.495 is 13.8 times 10 to the 8th. That's pretty darn close. I could try and find another 0.1 to add in there. Let's try these combinations and see what we get. So 5 Jupiters, 3 Saturns, 5 Uranus, and 1 Neptune. That's pretty darn close. Over here, it's going to show us the difference. We are a little off, but not by much. I mean, I guess 1 times 10 to the 7th meters is still a lot, but for our stacks here, when we're talking about numbers this huge, we're really not too far off. But we are shorter than the sun by 1 times 10 to the 7th. So let's see. Over here I see we have Venus is about 1 times 10 to the 7th. So we could add one of these and see how close we are now. Now we are a little bit over. We are a little bit taller than the sun by about 2.1 times 10 to the 6th. So maybe instead of adding one of these, maybe we add 2 of these. Because this would be about 5, and 2 5s would be almost 10 instead of 12. So let's try this. So we got it down to 2.4 times 10 to the 5th. So we are a little bit short of the sun, but much better than our first attempt, because 10 to the 5th is smaller than 10 to the 7th. All right, please make sure your warm-up is complete. If there's any notes that you need to include in your workbook for this lesson, please do so. Otherwise, with this digital lesson, just make sure you're following along and understanding what's going on, and you're good to go.